This is my video report for Lab 2 of the Physics 2211 course. The purpose of this lab was to compare the observed trajectory of a projectile with its predicted trajectory assuming zero and non-zero air resistance. The first model/fundamental physics principle involved was Newton's second law, or the momentum principle, which states that the net force on an object is equal to the rate of change of its momentum. Secondly, a projectile is an object that undergoes constant vertical acceleration due to gravity only. It has a constant horizontal velocity. Finally, air resistance, or the drag force, opposes the motion of an object. The magnitude of the drag force is proportional to the square of the speed of the object, and so it is a non-constant force. As for a quick preview of the results, the observed and predicted trajectories of the projectile were all roughly parabolic, and the trajectory predicted by the model assuming zero air resistance had a greater range, which is the total horizontal displacement, than the observed trajectory and predicted trajectory when accounting for air resistance. This is the formula for the momentum principle, and the variables are defined here on the right. From it, we can find the change in velocity, which we use to derive the velocity update formula and position update formula. These final two formulae will be used in the computational model. The net force on the projectile is the sum of the gravitational force and drag force. In the model assuming zero air resistance, the proportionality constant B is equal to 0, whereas in the model accounting for air resistance, B will be some non-zero value. Number 1, there will be some inherent assumptions of Newton's second law as follows. Regarding assumption number 2, gravitational potential energy is converted to translational and rotational kinetic energy. However, for simplicity, I'll assume that the rotational kinetic energy is negligible. Lastly, I'll ignore any motion along the z dimension. This way, I'll only need to analyze motion along 2 dimensions, which simplifies my calculations. These are the initial conditions for the position, velocity, and mass of the paper ball, as well as the height of the table. The system is the paper ball, and the surroundings consist of everything else, including the air and earth. As for the experiment, we crumpled a sheet of paper into a ball and measured the height of the table, which was the reference object used to scale the calibration stick and tracker. We began recording the video, then flicked the paper ball off the table, and stopped the video after the ball landed on the ground. To extract motion data from the video, I used the point mass function in tracker to locate the paper ball at each point in time. This produced a series of data points that were plotted as follows. We will pay attention to the trajectory, which plots the y position against the x position. These are the same initial conditions I mentioned implemented in code for the computational model. In the model assuming zero air resistance, I've set b to be 0. And in the model assuming non-zero air resistance, I've set b to be 0.0011, a value I obtained through trial and error. The total time that the ball spent in flight was 0.5 seconds, hence the header for the while loop. And here is the same net force formula and velocity and position update formula from before, implemented in code for the computational model. Here is the output of the code for both models. And here are the predicted and observed trajectories all plotted on the same graph. Note here that all 3 plots indicate a roughly parabolic trajectory, and the model assuming zero air resistance extends out further in terms of x position than the other 2 plots. Here's the physics explanation for why all 3 plots of the projectile's trajectory are roughly parabolic. These kinematic equations apply to motion under a constant net force and therefore apply to the model assuming zero air resistance. Note here that the equation relating the vertical and horizontal displacement is a quadratic polynomial, which is a parabola when graphed. The trajectory predicted by the model assuming zero air resistance had a greater range than the other 2 plots. This is because air resistance opposes the motion of the projectile, so a component of the drag force acts in the positive x direction. Therefore, the projectile moving in the negative x direction has a shorter displacement in the same amount of time. As for sources of error, because the paper ball was in the air for 0.5 seconds, I only captured its motion data from 15 frames. Any random error in point placement, which was done manually, had a relatively large effect on the overall trajectory. Any minor disparities between the observed trajectory and model accounting for drag are likely due to this random error. And since rotational kinetic energy was not accounted for by either model, the final predicted speed would have been slightly larger than the actual final speed. An object is at terminal velocity when a free-falling object experiences zero net force. Neither of my models predict terminal velocity because the velocity time graph would have to be horizontal. To find the object's terminal velocity, I'd place it in a steady upward flow produced by a fan, for example, and find the speed of airflow at which the object hovers. When an object hovers, it has a zero velocity, and so a zero net force acts on it. If the object were initially thrown straight up with the same initial speed as in the original experiment, the object would take longer to reach the ground, and this is because its initial vertical velocity in this new experiment is greater than its initial vertical velocity in the original experiment. Here are some calculations I used to verify my prediction. I used approximate, not exact values for the initial speed and total vertical displacement, but the final time for this new hypothetical experiment is significantly larger than the original time of 0.5 seconds. To conclude, the observed trajectory of a projectile and its predicted motion, assuming zero and non-zero air resistance, are all roughly parabolic. And the model assuming non-zero air resistance better fits the observed motion than the model assuming zero air resistance, which predicts a larger range than the actual value.